Okay, let's move into our next lesson here. So the first regular lesson that we're going to move into in our next unit here is on finding sums. We're going to learn about two well-known mathematicians, Gauss and Euclid, and there are two methods that are attributed to them for finding sums of the terms in a sequence. So for now, your prior knowledge for this should be arithmetic and geometric sequences and how to work with them. So if you need to go back and look that up or review for yourself, you can go ahead and do that now. Here's one warm-up I'm going to give you right now that will help you do some review for that. So, and don't forget to take notes. Fill in the missing terms for the sequence, assuming it is A, arithmetic, and then B, geometric. So this is kind of two separate problems, but we're using the same sequence here. So please go ahead and pause now, and then we'll go through the solution together. Okay, so let's start out with part A, assuming it's arithmetic. Now, there's different ways you could have approached this, of course. You could just kind of think in your head and try to work through the numbers. Either way, if you recall, I've got to add 1, 2, 3 things, okay? And we often call it D for difference if we're talking about an arithmetic sequence. To go from 9 to 72. Now, I also like to think of it like this. One single jump from 9 to 72 represents how much? Well, 9 to 72, we just subtract. So 63, right? So this is a distance of 63. And I don't know what this is. Again, I could call it D. And I have 3 jumps to make to go 63. You can kind of figure out in your head how much each of those jumps has to be. So if you did it that way, you can see that this is going to be, okay, well, 63 divided by 3 is 21. So 9 plus 21 gives me 30, plus 21 gives me 51. And sure enough, plus 21 again gives me 72. So the answer for A should be 9, 30, 51, 72. Okay? And you can go ahead and copy that, those notes down that we took. And I want to remind you here that this was adding for the arithmetic one, right? Actually, let's just rewrite this down here. So let's do it again, 9 blank blank 72. But in this case, we're actually not doing jumps based on addition, we're doing a geometric sequence, right? Based on multiplying. So 9 times 8 is 72. Well, one product of 8 is the same as, how do I split that 8 into 3 jumps? Well, if you remember, that kind of goes along with the cubed root, right? So the cubed root of 8, in this case it turns out to be nice, right, is going to be 2, right? Oops. 3 2's multiplied make one single 8. So we can kind of figure that out, and we can get that 9 times 2 is 18, and that times 2 is 36, and sure enough 36 times 2 is 72. And so my answer is 9, 18, 36, 72 for the geometric. I do want to remind you of something. Is you can set this up with equations as well. Okay, we've learned this in the past too. So based on this is more of like a visual diagram. I could have tackled the first one. I'm going to go ahead and erase this since you have it written in your notes. I could have tackled the first one by just saying, well, I know if I start with 9 and I add 3 D's to it, I get to 72. And then you can just solve this equation. If I subtract 9, I get 3D equals 63, just like I already worked out, and therefore D equals 21, and then I can just add 21 each time. And similarly for this, same idea what we can do here is start with 9 and realize that 9 times, in this case we'll call it R, we usually call it common ratio, right? So R times R times R. Well, R times itself 3 times is the same as saying 9R cubed equals 72. Therefore, dividing by 9 now, R cubed equals 8, and therefore R equals 2, and it still gives me the same thing. Okay, so there's our warm-up. Let's go ahead and jump right into our lesson. So, let's go ahead and look at a couple classic ways that have been developed to find sums with very specific patterns. We're going to start with one attributed to Carl Friedrich Gauss, who was a mathematician from the late 1700s. He lived until I think 1855, and he is very well known today for being one of the most important modern mathematicians. And I know that that doesn't seem super modern, but relatively speaking it is. Anyway, so there's a story that says when Gauss was young, and I don't know all the details of the story. One version of this I read was that he his class was maybe acting up or something when he was in first grade or something like that, and his teacher was annoyed at them, and so he gave them all this punishment. Or maybe he just, I like to think he gave it to them as a problem to challenge them from their learning addition. And he asked all the class to find the sum from 1 to 100 of all the whole numbers from 1 through 100. So 1 plus 2 plus 3 plus 4 plus 5, all the way until 100. And we're going to go ahead and learn a specific method today. Actually, we're going to talk about a few that can help us do this. But first, I want you to pause right now, and I want you to try to see if you can actually find an easy way to do this. Some of you who have already been in my class will have seen this type of sequence and maybe even remember a formula, though we'll get to that later. So go ahead and pause right now and try to tackle that in your notes. Okay, so we're going to talk about, I guess, I don't know, 3 different methods. So let's do method 1, and this is one where you hopefully would be familiar with it if you've been in my class. I'm going to simplify the problem a little bit for right now, and you'll kind of see why. Let's imagine that we have a staircase that's just getting bigger and bigger and bigger. You can see this staircase. We have one. This is 1 unit high, 2, 3, 4, 5, etc. So the total amount of blocks that are making my staircase is from the same sequence here that we're working with, right? And there's this really ingenious visual method, and again, if you've been in my class, you've seen it before, that we can use. Well, if I want to find an easy way to calculate the total number of blocks, here's one way that actually works. I'm going to double it. I'm going to take a second one of these, okay? And I'm going to go ahead and put these together. And you can see that this, if we make a double staircase, actually makes a rectangle. And I color-coded it so you can see what matches with what. Although actually, now that I look at this, I could have matched up some of the colors so that they do all be in the same rows with each other. But either way, oops, I lost one. If we double it, one of the staircases is half of this rectangle. So if we can find an easy way, well, rectangles are really easy to find the total number of squares, I guess, right? Because that's just area. Area is going to be length times width. Well, what staircase is this? This looks like it's up to 5. 1, 2, 3, 4, 5. And if I put these together, this rectangle actually has a height of 6 or a width of 6, depending on how you look at it. But we'll look at it like this. And it still has a width of 5, so it's 5 times 6, which is 30. Well, since this is half of that, it's 30 divided by 2, and so we have a total of 15 blocks here, right? So if you could kind of think of this as half, right, of this infinite staircase that's going all the way up, so that this last one has a height of 100, and that means this has 100, right? Well, I want to remind you, as soon as we stack the other one on top of this, that one adds on. That very first row adds on to the last row. So there's one more there, right? So if I were to actually double this, we can see right? And then we have all these blocks here. And this total height actually has a height of 101, doesn't it? So one way we can easily figure this out, which is really cool, is if we actually take 101, right? Height times width times 100, but it's going to have to be half of that. So I can multiply it by 1/2, or I'll just divide the whole thing by 2. And what this gives me is 101, I'm going to cancel out the 102, and then 50 times 50 And 101 times 50 is going to be, well, 100 times 50 is 5,000 plus 50. So it's going to be 50, 50. And that's a really cool way. Now, all the methods that we're going to talk about actually are really the same as each other. It's just thinking about them slightly differently. So let's go ahead and jump into another method here. Method 2, I don't know, I almost like to call this the rainbow method. So if I actually were to list out 1 plus 2 plus 3, and I find that a lot of students actually pick up on this themselves often. And I call it the rainbow method just because if I suppose I could use different colors, but I guess it doesn't really matter. Let me just grab my purple here. If you notice something really interesting, if you match up, right? I think if you start from the outside in, but if you match up the first and last number, and then the next one in, and then 2 in, and 3 in, and 4 in, watch what happens. 1 and 100 makes 101. 2 and 99 makes 101. 3 and 98 also makes 101. In fact, we get 101 all the way in when we match these up in this way. And where do you see 101 happening? Wait a minute, we saw 101 happening up here. I want you to look at something here. This right here, each one of those matchings, notice how we have 100 and 1. Well, that row right there has 100 plus 1, but actually so does this row, because this red guy up here is going to stack 1 on top later on, right? And so this is really just the same as that. But we can think of this in a different way, because we didn't really notice it there that much. I think what we did was we thought of it as a rectangle cut in half. But here, instead we can see the same exact thing as, well, how many pairs, since there's 100 numbers here, right? And we're pairing them up, how many total pairs of 101 are there? Oh, there's 50 of them, right? Because we're pairing all these 100 numbers. So we can see that this is the same as, I guess I'll use my blue again. It's the same as saying, well, we have 50 pairs making 101 each, right? So that just gives me 50 times 101, which is exactly the same as what I got a minute ago, and so we get 5,050 again, which is really neat. And lastly, I'm actually going to officially introduce you to what we call Gauss's method, and apparently this is attributed to him, and again, it's really the same. It's really the same thing. But I do want you to be familiar with each version of this. Gauss basically said, okay, well, let's call this sum S for sum, and 1 plus 2 plus 3, and then I'll just write it the way I've been writing it, 98, 99, 100. But then we're going to do something a little bit ingenious here. We're going to copy this again, but in reverse. And there's a reason why, because you can see when I pair these up, it's just like there and there that we just talked about, that we get all these pairs of 101. Now, we've learned that we can add 2 equations up with each other, right, and still get another true equation. So S plus S gives me 2S, and look what happens. We get 101 plus 101 plus 101. And again, we can just think to ourselves, oh, how many of those are there going to be? Well, in this case, there's actually 100 of them, right? And so we get 2S equals 100 times 101, and therefore, let's change to my blue color again. Therefore, the sum itself, because we can just divide by 2 now, is equal to 100 times 101 over 2, and what do you know? It still ends up being 50-50. So this last method is really the one that's called Gauss's method, but really these are all the same versions of each other, okay? And we'll be exploring problems related to this today. And also we're going to look at another famous mathematician from much earlier than Gauss's time and another method that's attributed to him. But first let's get some practice with Gauss's method. Okay, so I want you to actually tackle a few problems of your own using Gauss's method. Okay, so number 2 here, use Gauss's method to find the following integer sums. So A, B, C, and D. I definitely want you to do A and B on your own. Okay, I would really like those to be done on your own before you check your answers with me. And I'd really like you to take a good strong stab at C and D. Don't just spend 30 seconds on them, really actually spend some time on them to try to see if you can dig out an answer for them. Okay, they're a little trickier because this one's generalizing 1 to n, so it's actually going to turn into a formula. And this one's the even, so the way that we count how many pairs there are is going to be a little bit different, a little bit tricky, but you can still figure it out. Okay, so please go ahead and do this. Pause right now, and then we'll go through the solutions in a moment. So let's go ahead and go through these. I've already pre-written out kind of the long part so we can take care of this pretty quickly. So let's go ahead and start with 1 to 371. Following the same process, adding this together, we get 2s equals, well, look what each of these things as we lined it up in reverse adds to 372, right? Each of these things adds to 372. So what we have is just a bunch of copies of 372. And the question is, how many pairs do we have? Kind of like we asked before, right? And the one thing to think about here is, since we started at 1 and we're ending at 371, we just have 1, 2, 3, 4, 5, all the way to 371. There's just 371 pairs. So what we can shorten this to is 2s equals 372 times 371. Okay, because remember, there's 371 pairs of 372. I guess I wouldn't say, maybe I shouldn't say, I should say copies of 372, because once we've paired these up and added them, then they become 372. Okay, so that's how we want to think about this. And when we do this, okay, s equals, we're going to divide by 2. We get 69,006. I pre-calculated that for us. Okay, so you should check your answer for that. Let's go ahead and check our answer for this one right here. So again, we've started up at -3 and we've gone to 84. And same thing happens here as we get 2s equals, in this case they all add up to something less than 84 though. -3 plus 84 is 81. And you can surely see that the rest of these pairs add up to 81. So we'll just write it like that. We have a bunch of copies of 81. But again, we have to ask the question, how many copies of 81 are there, right? Well, this one's a little bit trickier actually to figure out, because we are going to have 2s equals 81 times however many of them there are, right? Like to shorten that. But we have to be a little bit careful, because we're not just starting at the number 1 to 371. You can see there's 371 things there. Well, if I'm going from -3 to 84, it's tempting to want to, kind of do what we did with our sequences before and just think, if I went from -3 to 84, oh, we can see that that was up by 87, right? But there's one little catch here with sequences like this, if we're not starting there, is we have this distance of 87 doesn't include, because what we're really asking is how many numbers are there from -3 to 84, not how far apart are -3 and 84. And hopefully that is something that you understand the difference between. How many integers are between -3 and 84? There's actually one extra, okay? So there's actually 88 integers here. And let's think of a simpler example. Let's say, how many numbers are there from 4 to 7? Well, there's not just 3. If I'm actually wondering from 4 to 7, there's 4, 5, 6, 7, right? So there's 3 plus 1. There's always one more. So it's kind of a long explanation maybe, but I want you to be careful here. The number of integers is not the distance. It's actually always the distance plus 1. So how many 81s are there here? Well, if we went from negative 3 to 84, and there's a distance of 87, there's 88 integers. So it's 81 times 88. And therefore, S is equal to 81 times 88 over 2. And I did that one as well. It's going to give me 3564. So you can go ahead and check that. The one thing you may have missed, like I said, is accidentally thinking there's 87 of those instead of 88. Now we can get to these two that are a little bit trickier. I'm hoping you've really tried to take a stab at doing them on your own first. But let's go ahead and look at the setup here before we do this one. If I want the integers from 1 to n, well, it's the same thing, 1, 2, 3, all the way up to n. You may have forgotten or not remember or unsure about how do I express integers that come before n. Don't forget, it's simply just, if I want to know 1 before anything, it's minus 1. So the integer before n is n minus 1. And then the one before that is n minus 2, n minus 3, etc., etc. So I can do the same thing here. I can line it up forwards and backwards and add them together. And I'm going to get 2s equals, now here's what the trick is. If I line these up, each piece, 1 plus n is n plus 1. 2 plus n minus 1 is also n plus 1. In fact, actually, this is always 1 more than that, so this minus and that plus always is going to end up as plus 1. So what we have is n plus 1 times something, right? The good thing about this one is it's not as tricky as this one to figure out how many total things there are, because we're just going from 1 to n, which means there's just simply n total of those things. And this hopefully is a formula you're familiar with if you've worked with other problems before, especially again if you've been in my class. And therefore, if we divide by 2, we get n plus 1 times n all over 2. We typically put the n first, because n is, represents a number 1 smaller than n plus 1 over 2. And this is a really helpful formula now, because, for example, if I want to go back here, instead of repeating that whole process, this now gives me a formulaic way, we basically just proved it, to calculate that. I could have just plugged in 371 and then multiplied by 372, which is exactly what I did, and then divided by 2. Now let's get to one that's a little bit trickier than all of these have been so far, I think. And again, I'm hoping that you've spent some time trying to tackle this one on your own first, if that's really important for your learning. Well, let's start by doing the same thing, okay? Because we're going to have to just do the same thing as we did here. It was a little tricky figuring out how many of these things there are. You can probably tell. So if we're doing the evens from 4 to 102, it's not just 4, 5, 6. It's just 4, 6, 8, and then 98, 100, 102, right? And you can probably tell here, whoops, that they still have the same constant sum, all these pairs, right? Okay, so 106, 106, 106, 106, 106, all the way across. So again, we get the same thing where we're saying, okay, well, 2s equals 106 times something, right? And again, my question is, how many 106s are there? And this is a little trickier because it's not, it's all the evens, right? It's not just every integer between. And again, we have this thing happening where it's not just straight up the distance either. I'll give you kind of how I think about this, and you can play with it on your own or think of it. But what we're starting at is 4, right? And then we're going all the way to 102. Now the literal distance of that is 98, right? Does that make sense? The only thing is, it's every even, so you probably can guess that that's going to be half as many evens. We're not, like the literal distance from 4 to 102 is 98, but just evens, it's half of that is 49, right? But if we just remember the same thing we did before over here, that's the distance, but because we're actually counting the first number we're starting with, you have to add 1, and it's actually the same thing, so it's actually going to be times 50. Another way to think of it is, if we start with 4, we can think of it as like a linear equation. If I start with 4 and I add 2, because isn't that how I get even numbers? Just start with an even number and just add 2 continuously. But how many 2's do we add? We're adding 49 of them. That's kind of what we were saying right here, right? If we add 2 49 times, we're going to actually get to 102. But we still had to start with 4, right? So there's 49 different numbers here, but if we include the 4, there's actually a total of 50. So that's another way to think of it, kind of like here. Okay? So anyway, in the end here, if we figure that out and we divide by 2, we get our total sum is going to be, I'm going to cheat because I did this ahead of time, 2,650. Okay, so those are examples and everything for using Gauss's method. Okay, now there's one final conclusion that I want to make with you here about Gauss's method, and it's really important. All these sequences we've worked with here to find the sums, to add them up, however many terms. Remember, we can add whichever terms I want in a sequence. What types of sequences are these? All the ones. Even this one here. You'll notice this one's increasing by 2 each term, right? All these are one of these 2 types of sequences, arithmetic, okay? So an important takeaway that you need to write down right now is that Gauss's method, okay, is used for arithmetic sequences, okay? I guess I should say sums of arithmetic sequences, just to make sure we're clear we're talking about adding up the terms in an arithmetic sequence. So, in the next video, we're going to take a look at a totally different method, and you probably already guessed that it's going to deal with adding up the terms in a geometric sequence.